Electronegativity and its changes. This is today's lesson. In this lesson, we are going to learn definition of electronegativity, unit of electronegativity, electronegativity change along a period, and finally, electronegativity change along a column. So, no more delay, let's get started. The very first point is definition of electronegativity. Let's see what is electronegativity. Let us consider it's a compound, covalent compound. AB is a covalent molecule. This is covalent bond. Electronegativity is related to covalent molecule or covalent compound. Here, AB is a kind of covalent compound or covalent molecule. This is nucleus of atom A, and this is outermost shell of atom A. As this is covalent bond, one pair of electrons, which is called covalently bonded electrons or shared pair of electrons. This is atom B and this is its outermost shell, AB molecule. Here, electrons negatively charged, nucleus positively charged, this nucleus positively charged. These electrons, covalently bonded electrons, will be attracted by both the atoms, especially both the nuclei, because nucleus is positively charged, electron is negatively charged. That is why covalently bonded electrons will be attracted by both the atoms, especially both the nuclei. This attraction is called electronegativity. Electronegativity is denoted by Greek letter chi. What is electronegativity? Covalently bonded electrons will be attracted by both the atoms. This attraction is called electronegativity. Definition of electronegativity is the relative ability or attraction of covalently bonded atoms to the covalently bonded electrons towards themselves is known as electronegativity. Attraction of atom of any element to the shared pair of electrons in a covalent molecule is known as electronegativity. Electronegativity is denoted by Greek letter chi, as these two atoms from two different elements, element A and element B. So, effective nuclear charge of atom A and atom B will be different because these two atoms are from two different elements, element A and element B. As these two atoms are different, their electronegativity, that means attraction to the covalently bonded electrons, will be different because their effective nuclear charge will be different. Suppose electronegativity of atom A is higher than B, then covalently bonded electrons will move towards A, because we said electronegativity of A is higher than B. That is why covalently bonded electrons will move towards A. As a result, over A, partially negative charge appears, and over B, partial positive charge appears. Here, covalently bonded electrons move towards A. That is why A becomes partially negative in charge and B becomes partially positive in charge. That means now in this molecule there are two poles. One is negative pole, another one is positive pole. Two ends, two poles. That is why this molecule, AB molecule, is a kind of polar molecule. That means AB molecule has a polarity. It has two poles, positive pole and negative pole, because of the electronegativity difference. Again, let's see what is electronegativity. Electronegativity is defined as the relative ability to attract the shared pair of electrons of atoms in a covalent molecule towards themselves is known as electronegativity. Electronegativity is a relative term, that is, one's electronegativity is lower and another one's electronegativity is higher. This is simply a relative term. Now let's see what is the unit of electronegativity. Now the point is unit of electronegativity. Let's see the matter. Let us consider it's a covalent molecule in which covalently bonded electrons will be attracted by both the atoms, by atom B and by atom A. As these two atoms are from two different elements, their attraction to the covalently bonded electrons will be different. That is, electronegativity is simply a relative term. That is why electronegativity has no unit. American chemist Linus Pauling designed a scale of electronegativity that ranks elements with respect to each other. For example, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Electronegativity of francium is the least, that is 0.7. Again, let's see elements of column 17: fluorine, chlorine, bromine, iodine, astatine, tennessine. Here, electronegativity of fluorine is 4.0, which is the highest electronegativity among the elements. That is, francium is the element with the least electronegativity and fluorine is the element with the highest electronegativity. This is a relative term, no unit of electronegativity. Let's move on to the next point. Electronegativity change along a period. Let's see elements that belong to period 2. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and finally neon. Neon is a kind of inert element. That is why it is kept out of consideration. Here, electronegativity of lithium is 1.0, beryllium is 1.5, boron 2.0, carbon 2.5, nitrogen 3.0 or specifically 3.1, oxygen 3.5, electronegativity of fluorine is 4.0. That is, electronegativity from left to right along a period increases. Electronegativity increases along a period from left to right. What is the reason behind this? Let's try to find the matter. Here, atomic number of lithium is 3. This is 4. 5 for boron, 6, 7, 8, 9 for fluorine. That is, from left to right along a period, atomic number increases. Let's see here. Suppose this is an atom of element of second period. Here, this is another atom which is from another period. About this atom of any element of second period, if we go from left to right, then we see atomic number increases. That means number of protons in the nucleus increases. That is, effective nuclear charge increases from left to right. As effective nuclear charge increases from left to right with the increase of atomic number, that is why electron covalently bonded electron attracting tendency increases from left to right, as effective nuclear charge increases from left to right. So from left to right, electronegativity increases as effective nuclear charge increases with the increase of atomic number. This is one point. Another point is, from left to right, we know atomic sizes decrease. Suppose this atom decreases to this atom. Here, distance between nucleus and covalently bonded electrons is this. But when the atom is smaller in size, then distance is decreased. With the decrease of distance between nucleus and covalently bonded electrons, attraction increases. That means electronegativity increases with the decrease of atomic size. As atomic sizes decrease from left to right along a period, electronegativity increases along a period from left to right. That is 2 points. One is effective nuclear charge increases with the increase of atomic number from left to right. That is why electronegativity increases. Number 2, from left to right, atomic sizes decrease. When atomic sizes decrease, distance between nucleus and covalently bonded electrons decreases, and then attraction increases. That means electronegativity increases from left to right along a period. Let's move on to the next point. Now the point is change of electronegativity along a column. Let's see elements that belong to column 17. Fluorine, chlorine, bromine, iodine, astatine, tennessine. Electronegativity of fluorine is 4.0, chlorine 3.0, bromine 2.8, iodine 2.5, astatine 2.1. Here we see that from top to bottom along a column, electronegativity decreases. What is the reason behind this? Here, atomic number of fluorine is 9, chlorine 17, bromine 35, iodine 53, and so on. That is, here as well, from top to bottom along a column, atomic number increases. But in case of column, electronegativity decreases. We have learned that along a period, with the increase of atomic number, effective nuclear charge increases, electronegativity increases. But along a column, with the increase of atomic number, electronegativity decreases. Why? Let's try to find the matter. Here we see that electronic configuration of fluorine is 1s2, 2s2, 2p5. That is, fluorine has two shells, 1, 2. First shell contains 2 electrons, second shell contains 7 electrons. Let's see about chlorine. Nucleus of chlorine, in which first shell contains 2 electrons, second shell contains 8 electrons. In case of chlorine, third shell contains 7 electrons. Chlorine 17, 1s2, 2s2, 2p6, 3s2, 3p5. 10 electrons, 12, 17 electrons. That is, in case of chlorine, there are 3 shells. First shell with 2 electrons, second shell with 8 electrons, third shell with 7 electrons. But in case of fluorine, 2 shells. First shell with 2 electrons, second shell with 7 electrons. In case of column, from top to bottom, we see that number of shells increase. That is, for fluorine 2 shells, for chlorine 3 shells, for bromine it will be 4 shells. When number of shells increase, then suppose this is fluorine, first shell, second shell. Here, suppose this is chlorine, first shell, second shell, third shell. In case of fluorine, only one inner shell is here. This shell creates shielding effect. That is why attraction between nucleus and covalently bonded electrons is barred by the inner shell electrons. When we move to chlorine, that is from top to bottom, then number of inner shells increase. That is, shielding effect increases. Nucleus cannot attract these covalently bonded electrons towards itself properly because of the presence of inner shell electrons. That is, simply from top to bottom along a column, effective nuclear charge decreases because of the presence of inner shell electrons. This is number 1. Number 2, if we move from top to bottom, atomic sizes increase. When atomic sizes increase, then covalently bonded electrons and nucleus distance increases. When distance increases, attraction force decreases. with the increase of the distance. When distance increases, attraction force decreases. That is, electronegativity decreases. That means from top to bottom, atomic sizes increase, distance between nucleus and covalently bonded electrons will be increased. Ultimately, electronegativity will decrease. Again, from top to bottom, number of shells increases, effective nuclear charge decreases. That is, attraction between nucleus and covalently bonded electrons will decrease. That is, electronegativity will decrease. Electronegativity increases along a period from left to right because of the increase of effective nuclear charge, and it decreases along a column because of the decrease of effective nuclear charge and increase of size of atoms. Hydrogen chloride is a kind of covalent molecule in which electronegativity of hydrogen is 2.1, but electronegativity of chlorine is 3.0. A huge difference in electronegativity between hydrogen and chlorine. As a result, covalently bonded electrons move towards chlorine, and ultimately chlorine achieves partially negative charge and hydrogen achieves partially positive charge. Because of the electronegativity difference between hydrogen and chlorine, electronegativity of chlorine is higher. That is why covalently bonded electrons or electron cloud will move towards chlorine. That is why chlorine becomes partially negative in charge and hydrogen becomes partially positive in charge. And it has two poles, negative pole and positive pole. Molecule with two poles. That is why it's a kind of polar molecule. Polar molecule because of the electronegativity difference. This is all about electronegativity and its changes. If this lesson benefits you a bit, then please subscribe to the channel. No more today. Thank you very much.